Okay, hello everybody. This is section 13.6, colligative properties of solutions. This is part 2 of the lecture video for chapter 13, properties of solution. So the first thing we need to do is to define colligative properties. These are properties which are dependent on the number of solute particles and not on their chemical nature or identity. Okay, so anything that is dependent on the number of particles, solute particle, is referred to as the colligative properties. There are four main examples of colligative properties. These are freezing point, boiling point, osmotic pressure, and vapor pressure. We are going to discuss each one of these colligative properties in turn, and we will focus first on the definition and the characteristics of these physical properties, and then we will take a look at some examples or applications of these properties when it comes to basic properties of solutions. So the first one we're going to discuss is called freezing point depression, or basically the one that I've outlined here as freezing point. So freezing point depression, the reason they call it freezing point depression is because the freezing point of the solvent is usually lowered after we add the solute particles to it. So that lowering of the freezing point is referred to as depression. So freezing point depression is when the solvent has a lower freezing point compared to the solution itself. So let's go to the next page. Okay, now the freezing point equation that we need to use for solving some of the problem is given in equation 1. Delta TF is equal to minus KF times M. Now the delta TF is a change in freezing point. So basically it's defined as the freezing point of the solution minus the freezing point of the solvent, and it is measured in degrees Celsius. So remember, the TF stands for the freezing point temperature. So that's basically the freezing point of the solution minus the freezing point of the solvent. That's that difference. KF is called molal freezing point depression constant, and it's basically tabulated for different solvents. Table 13.6 in your textbook has a listing of several KF values for various solvents. Now M, as we know, it stands for molality, moles per kilogram. That's the unit of molality, and we will be using this equation later on. Now the second physical property, which is the colligative property that we're discussing today, is called boiling point elevation. Again, the reason they call it the boiling point elevation is because the boiling point of a solvent is observed to be elevated after we add the solute particles to that solvent. So if you compare the boiling point of the solvent by itself, a pure solvent, and then solvent plus solute, or the solution, you'll see that the boiling point of the solvent is going to be higher compared to the solution, which is a combination of both solvent and solute. Okay, so the equation for that is delta TB equal to KB times M. Now, note that there is no negative sign here because there's an elevation in the boiling point compared with the negative sign that we had for equation 1, which basically refers to a depression or a lowering of the freezing point. So let me just go to the next page, and then we'll be basically looking at another colligative property. But first, let's just define the symbols again. Delta TB, as we defined it earlier, is solution minus solvent. But in this case, it's the boiling point of the solution minus the boiling point of the solvent in degrees Celsius. Kb is called molal boiling point elevation constant. Degrees Celsius per molality is the unit. And again, they are tabulated. Table 13.6 in your table, in your textbook. M stands for molality, moles per kilogram. And again, I've mentioned that there is no minus sign in boiling point equation. Now, osmotic pressure. Again, we will come back to this equation later on. Osmotic pressure is given by equation 3. Pi stands for osmotic pressure. M stands for molarity. R is a gas constant, 0.0821 liter atmosphere per mole Kelvin. That will be given to you. You don't need to memorize that, but if you do, that's fine. T is the Kelvin temperature, not Celsius temperature, not centigrade temperature. So it's basically degrees Celsius plus 273 to get you the T that you need for the equation 3. So equation 3, the temperature must be expressed in Kelvin. The reason that it must be expressed in Kelvin is because of the unit of Kelvin here in R. Okay, so the next page shows the vapor pressure lowering equation, but the vapor pressure basically is for the solvent above the solution is lowered, is less compared to the solution due to the solute particles. So basically the equation tells you that the vapor pressure of above the solution, which is Pa, is less than the vapor pressure of the solvent, which is Pa0. And that you can see it from that equation 4, because the pure solvent vapor pressure, or Pa0, is multiplied by XA. XA stands for the mole fraction of solvent. So when you multiply the vapor pressure of the pure solvent by a fraction, the result, which refers to the solution, is going to be less than Pa0. Now, everything in the right-hand side of equation 4 refers to solvent, so don't forget that. So basically, XA is the mole fraction of the solvent, Pa0 is the vapor pressure of the pure solvent, and Pa refers to the solution. Okay, now we can take a look at some actual application of these colligative properties. In other words, we're going to use them in some simple calculations. So the first one is sample problem 13.8, page 561 in your textbook. Basically, this is a problem that describes the addition of 1 kilogram of ethylene glycol, which is the main component in the antifreeze compartment of your car, being added to some water, 4,450 grams of water. So we have 1 kilogram of ethylene glycol added to water, and the question is, what is the freezing point and the boiling point of the solution form when we form that solution? Okay, so basically what we are looking for is the TF of solution and the TB of solution, just to be compatible with the notation that we have been using. Okay, and given to us is the KF, the freezing point depression constant for water, and the KB, or the boiling point elevation constant. So they have been given to us. One of them is 1.86, the other one is 0.512. Now, what you should also know is that the freezing point of water is, of course, 0 degrees Celsius. The boiling point of water is 100 degrees Celsius. Okay, so now that we have all this information, we should be able to calculate the boiling point of the solution. So remember, the equation, the freezing point equation, is TB solution minus TB solvent equal to KB times M. So what we're looking for is TB solution. So I'm gonna take the TB of solvent to the other side, and we already know that's 100 degrees Celsius. KB is given to us. Molality is what we have to find first. So molality is moles of ethylene glycol divided by the kilogram of water. So we have 1 kilogram of ethylene glycol. We need to convert it to grams first using this conversion factor. And then from there, we need to convert it to moles using the molar mass, which will be given to you. Okay? So 1 kilogram is 1,000 grams. And then we divide that by the grams or per mole, which is the molar mass, 62.07. And that gives us 16.1 moles. And then we also have to convert the grams of water to kilograms of water, which for the denominator of the molality equation. So 4450 grams of water divided by 1,000 to get it into kilograms, and that gives you 4.45 kilograms. Now that we have the moles and the kilograms of the solvent, we can easily calculate the molality to be 3.62 m. So that's one thing that we need. So that's basically the m here in this boiling point elevation equation. Now let's go to the next page. So now we have KB, we have molality, we have the boiling point of solvent. We can easily plug everything in and find the boiling point of the solution to be 101.85. Now notice that the boiling point of the solution has gone from 100 degrees Celsius, which is the pure water, to 101.85. Therefore, because of the addition of ethylene glycol, we have basically increased the boiling point of the solution, and that is what we refer to as the boiling point elevation. So it's gone from 100 to 101.85. Now to calculate the freezing point of the solution, we proceed along the same lines. The TF of the solution is going to be minus KF times M plus TF of the solvent. So I'm looking for TF of the solution. I'm solving for TF of solution. Again, everything is given. TF of the solvent, we already know it's 0. The KF is 1.86. Molality, we already calculated in part A to be 3.62. And we plug in everything and we get negative 6.73. So again, the freezing point of the solution is now negative 6.73, which is compatible with the concept of freezing point depression, because it's gone from 0 to negative 6.73. So therefore, that's a depression, or that's a lowering of the freezing point. The next problem deals with the calculation of molar mass from colligative properties. Now, in this problem, a certain amount of a hemoglobin protein that binds with oxygen in body cell is dissolved in water to make 1.5 milliliter of solution at 5 degrees Celsius. The osmotic pressure is measured to be 3.61 torr, and the question is, what is the molar mass of the protein? Now, to calculate the molar mass, we have to divide the grams by the moles. The grams of the protein is given 21.5 milligrams, so that's basically can be converted to gram, which is 0.0215. So basically, we need the gram to divide it by mole to get the molar mass. So that number is given. In other words, we have to convert that milligrams to grams. We have that. And the next thing is to find moles. The moles must be calculated from molarity. In other words, in this equation, if you rearrange this to solve for M, M becomes pi divided by RT. So let's take a look at the next page and see how we can calculate the M so we can calculate the molarity. So in the next page, you see that R is given to us as 0.0821, but we have to do some unit conversion, because the pressure is given to us in units of torr and needs to be converted to atmosphere because R is in atmosphere. And also the temperature needs to be converted from Celsius to Kelvin because again, the unit of R carries Kelvin, not Celsius. So this conversion factor of 1 atmosphere equal to 760 torr is used here to convert the torr from 3.61 to 0.00475 atmosphere. So this is the conversion factor that you're using. And again, this conversion factor will be given. The temperature has to be converted to Kelvin, so simply add 273 to that, and that brings it up to 278 Kelvin. So now we plug in everything in this equation to find molarity. Why do we need molarity? So we can find the moles. Why do we need the moles? So we can find the molar mass. So everything is given here. We plug in everything now. R is 0.0821, T is 298. Well, actually that should read 278. That should read 278, okay? Because the temperature is 278. Okay, so this should be 278, not 298. And this is 0.00475. So that the answer is correct though. The answer is 2.08 times 10 negative 4. It's just you have to make a correction here. This is 278, not 298. Okay, once we have the molarity, we know that from the molarity equation, if you multiply the molarity by liter, you get the moles. And that's why we wanted to find the molarity, so we can multiply it by the volume of the solution to get the mole. Now we have 1.5 milliliter of the solution. We need to convert it to liter. Okay, so 1 liter is 1,000 milliliter. We get this number for the liter of solution. And now we have to multiply this by the molarity to get the moles, right? Molarity times liter. Okay, so let's take a look at the next page. And you see at the top of the page that moles is molarity times liter. That's 3.12 times 10 negative 7 moles. Now that we have calculated the moles, we can easily plug in the numbers in the molar mass equation, grams divided by moles, to find this number for the molar mass of the protein. As you can see, this is about 68,000 or 69,000 grams, which is a big number when it comes to molar masses, because usually the molar masses that you're dealing with here in chemistry, they really lie in the 0.001 all the way to maybe 70, 80, 90, in that range. But this one is about 69,000 grams for 1 mole. Now, the reason for that being that we are dealing with a macromolecule, biologically important protein that has a large sequence of a carbon and hydrogen repeating in the monomers, and it's a huge structure when it comes to other components like atoms and molecules in the cell. So this is a big molecule. So most proteins, they have high molecular weight or molar masses. The follow-up problem for this is also given to you here in the slide, 13.9a, 13.9b. Please take a look at those follow-up problems. But mainly the osmotic pressure problems, they deal with the calculation of molarity first, and then using that molarity to multiply it by the liter to get the moles, and then from there calculating the molar mass. Okay, now the next problem deals with Raoult's law to find vapor pressure lowering. Now, we didn't mention this before, but I think I forgot to mention it, but the vapor pressure lowering equation given by equation 4, PA equal to XA times PA0, is also known as Raoult's law. So that's just another name for PA equal to XA times PA0. The first person who came up with this equation was a scientist by the name of Raoult. and now it bears its name, Raoult's law. Okay, so this sample problem basically is about 10 milliliters of glycerol, C3H8O3, being added to 500 milliliters of water. The vapor pressure of water is 92.5 torr, and the density of water at that temperature is 0.988 gram per milliliter. The density of glycerol is 1.26 gram per milliliter. You may ask why the density of these two components have been given to us. Well, we use the density, as you will see later on. You use the density to convert from milliliters to grams using the density equation, right? Okay. So we start with the Raoult's law, or vapor pressure lowering, PA equal to XA, PA 0, XA being the mole fraction of solvent or water, PA 0 being the vapor pressure of pure water, 92.5 torr. Okay. Now in this equation, we don't have to convert torr to atmosphere or anything else, because the final result that we're going to get is still going to be in terms of torr. Okay. Now, if you have, for example, any problem dealing with torr, and then the R being given to you, then you know that you have to make some changes, but or some conversions. But here R is not given, so we'll just use 92.5 torr. Okay, so milliliters of water times density of water gives you the grams of water. Grams of water divided by the molar mass gives you the mole. So that's the basic strategy here. Okay. We are using the Raoult's law, XA times PA 0. XA is the mole fraction of water. But of course, if you want to calculate the XA, which is the X of water, you need to use this equation, moles of water divided by the total number of moles. So that's why we are trying to get the moles of these components so that we can plug it in here to find X. The molar masses are given, the densities are given, everything is given. So we're going to just use simply this chart here to go from milliliters to moles for the two components that we have. And after we substitute all those numbers there, we find 27.4 for water, 0.137 for glycerol, and the XA basically becomes 0.995. If you multiply that by PA 0, which is in this equation 92.5 torr, the PA, or the vapor pressure of water above solution, becomes 92.03. And the difference now is that basically the pure water, before we added the glycerol, had a vapor pressure of 92.5, and then when you add the glycerol, it becomes 92.03. So the difference between that and the solution is 0.461 torr. And as you can see, this is also referred to in your textbook as the delta P, but you don't have to worry about that part. We can just call it difference in vapor pressure. The follow-up problems are given, and we are basically finished with this chapter, properties of solution, and I will try to assign some Connect homework problem for you tomorrow. So tomorrow, be on the lookout for the for this video and also some Connect homework problem. Until Thursday, have a good day. I'll see you then. Bye.